Welcome everyone. I'm delighted to kick off this series of presentations. The title is The Next Frontier for UCLA Astronomy with the James Webb Space Telescope. I'm particularly delighted because this is the second event of a two-part series, and in the first event, you might remember, we didn't have JWST data because it was prior to the end of commissioning. In this one, we will actually see some JWST data. So, let's see. Okay, so this is a brief outline of my talk. I will give a brief introduction for those of you who are not familiar with JWST, talk about the launch and commissioning, which took place earlier, at the end of 2001, beginning of 2002, then give you some summary of how JWST is working, why it's so powerful, and describe some of the very first things we saw from JWST, the early release observations and the early release science programs. And then I will introduce the speakers of today who are presenting the first results from Cycle 1 programs. So Christmas of 2021 was a great day for me. I've been waiting on this since I was a little kid, the launch of JWST, and it happened exactly in the early morning of December 25th, 2021 from French Guiana. Is this playing now? I hope so. It doesn't seem to be playing. Move the mouse. Oh, there you go. Okay, so you don't hear the audio, but basically there's a French gentleman counting down from 10 to 0 in French as the engines are turned on. And this is the quite impressive launch from French Guiana, an Ariane 5 rocket lifted off. And the launch was just perfect. It couldn't have gone any better. The launch was actually one of the risk factors for the mission. We didn't know how well it would work, and we didn't know how precise it would be, and it turned out that it was extremely precise. And that means that the lifetime of the observatory is potentially longer than specs, just because the launch was so successful. And after launch, it started a long journey from Earth to a point called L2. This is about 1 million miles from Earth. And during the launch, the satellite deployed its solar panels to get power. And then there were some critical junctures, like when it deployed the secondary mirror, the sun shield, all these things that potentially could have gone wrong and instead went great. So when finally they arrived at L2, the spacecraft was ready for commissioning, which lasted about 6 months and ended at the end of June. So why is it JWST so revolutionary? There are several reasons. One is that it's a very large mirror, 6.5 meters, so much larger than Hubble, 7 times the area of Hubble. And the other important thing is that it works in the infrared. It's capable of detecting light that has longer wavelength than visible light, out to 28 micron. And we'll see why that's important. In addition, it has a very complex set of instruments, the most complex instruments ever flown into space. And why is infrared so important? The reason why infrared is so important is that infrared allows us to see things like the distant universe. As we will see, as light travels through the universe, the wavelength of light gets stretched, and so optical and UV light gets stretched into infrared. Allows us to see through dust, because dust is more transparent in infrared. And for example, we as humans and Earth, we emit radiation at about 12 micron. This is the radiation that comes from our bodies at about room temperature. And so if we want to detect planets, it's important to be able to look in the infrared. And also molecules, which may be signature of life, like oxygen and water, in the atmospheres of exoplanets, those are typically found in the infrared. So for a number of reasons, the infrared capability is essential. And so being at L2 allows the telescope to be extremely cold and therefore be able to detect this infrared radiation with extreme sensitivity. One important thing is that JWST is effectively a time machine. Light travels at a finite speed. Light is fast, but it's not infinitely fast. And so when we're looking at the very distant universe, if you're looking at the source that is, say, 13 billion light years away, the light that we're seeing left the source 13 billion light years ago. In a similar way as when we look at the sun, we see how the sun looked 8 minutes ago. When we look at the distant galaxy, we see how the galaxy looked 13 billion years ago. Now the universe is about 13.7 billion years ago. So with JWST, we can get pretty close to the Big Bang, and we have the hope to discover the first stars and first galaxies ever to be born in the universe. This was one of the science drivers for building JWST. The problem, however, is that when you try to see the very early universe, the universe expands, and as the universe expands, light stretches. And so light that starts in the optical or ultraviolet gets to us in the infrared. So this early universe would not be visible with Hubble because Hubble does not have the infrared sensitivity. So you need to go into the infrared. And one of the first images that we saw from JWST was this one. This is commissioning data, is an image sharpness check. And what it shows, what these images show, that JWST is sharper than SPECS. So not only the launch was perfect, but also the optics was perfect. Some of you may remember that when Hubble was launched, there was aberration. All the images were distorted. With JWST, the opposite happened. The telescope performed better than SPECS, which was amazing. And one of the first papers that came out is this paper characterizing the spacecraft at the end of commissioning. And there are two sentences highlighted in red. One says that the science instruments perform better than expected, so it's more sensitive than expected. And the other very important thing is that it has enough propellant on board to last at least 20 years. There were concerns that the mission may be limited to 5 years by the propellant on board. Instead, the launch was so accurate that the mission potentially can extend 20 years or more. So finally, on July 12, 2022, you might remember there was a press conference from the White House where the first images were released. This is one of the first images. And you can see here a comparison of JWST data in the middle with the previous infrared space telescope, of course, Spitzer's. This is the same part of the sky, and you can see the sharpness of JWST, just incredible. So it's much sharper, much more sensitive than anything we've ever had before. This is another comparison. On one side you see JWST, on the other side the previous infrared space telescope. Clearly the difference is stunning. But the thing that is, to me, was, almost made me cry, was when I saw this thing. So this may not mean to you as much as it means to me, but these are oxygen lines and hydrogen lines from the very early universe. These are lines that tell us that oxygen had already been formed a few 100 million years after the Big Bang. And this is something we could have only dreamed of detecting before JWST. And this was seen in the very first spectra taken with JWST. So this was extremely promising, telling us that there was a rich universe there to be discovered. So as part of the science of JWST, the Institute and NASA set up something called the Early Release Science Programs. Those were programs designed to enable the community to get rapid access to the data. These programs were selected in November 2017, spanning all areas of science. 13 such programs were selected, and the idea was exactly to inject in the community public data as quickly as possible for everyone to understand how the instrument was performing and learning how to use this telescope. And I was particularly lucky to be one of those, awarded one of those programs. And to me, this was a lifetime dream. So I went to my first conference in 1998, when I was starting my PhD about the science justification for the next generation space telescope. That's how it was called back then. And 24 years later, I finally got to see the data. So, but enough about me. What we're here to discuss is Cycle 1 programs. So there were more than 1,000 proposals submitted to use this telescope. Of course, everyone wanted to use it. The oversubscription was more than 4 to 1. So there were 4 times as many requests as possible. And UCLA was one of the most successful institutions in the world. We led 6 programs plus 1 early release science program. This is quite impressive. And those are the 7 programs. And you heard about 4 of them in the previous installation of this talk. That was before we actually got the data, so you didn't get to see the data. Today you will hear about the other 3, and now you also get to see some of the data. So I think this is quite exciting. So the 3 principal investigators we will hear from today are listed in order of distance to the astronomical sources, coming from the galactic neighborhood. We'll have Matthew Hosek, he's a postdoctoral scholar here at UCLA. Then distinguished Professor Gene Turner, talking about nearby galaxies. And we will end with Guido Roberts-Borsani, talking about very distant galaxies seen in the early universe. So, without wasting any more time, Matthew, please, the field is yours.
Well, as Tommaso said, my name is Matt Hosek. I'm a postdoc and Brinson Prize Fellow here at UCLA, working with the Galactic Center Group. And today, I'd like to talk about how we plan to use JWST to study star formation at the very heart of our Milky Way galaxy. In particular, we'll observe two clusters near our galactic center, the arches and quintuplet clusters shown here, to gain a new understanding into how stars form. Okay, so to start, we live in the Milky Way galaxy, which is a collection of hundreds of billions of stars that are gravitationally bound and orbiting a common center. Now, as you can see from this artist's depiction of the Milky Way, the Sun, we're located roughly halfway towards the edge of the galaxy, some 27 light years away from the galactic center. This puts the Sun...
27,000.
Oh, yes, 27,000. Sorry, I misspoke. 27,000 light years. Oh boy. Yes, thank you. 27,000 light years from the galactic center. At any rate, this puts the Sun in the part of the galaxy we call the galactic disk, which in this drawing is the bluish area where you see the spiral patterns of stars. So when we look at stars across our galaxy, we find that most of them are billions of years old, like our own Sun, which is 4.5 billion years old. But there are regions where we see stars still forming today, or we see stars that have formed in the recent past, which in astronomical terms means within the last few million years or so. And you may have seen images of these beautiful star-forming regions in the past because they really make for wonderful displays on our night sky. Examples include the Orion Nebula, the Eagle Nebula, and the Carina Nebula. Now, by studying these and other star-forming regions, we can learn a lot about how stars form. And we've learned that the basic story goes something like this. Now, we first start off with a cloud of gas out in space, which we call a molecular cloud. These molecular clouds are abundant in our galaxy, and we can find them just like we can find stars. Now, normally, we have a molecular cloud. It exists in an equilibrium, or a balance between the inward-directed forces and the outward-directed forces. The main inward-directed force is that of gravity, right? That's the same force that keeps us attached here to the Earth. The main outward-directed force is primarily gas pressure, which is analogous to the force that causes a balloon to inflate when you blow it up. So as long as these two forces are in balance, nothing will happen, and the molecular cloud will exist happily out in space. But if certain conditions are met, that inward gravity force can overtake the outward pressure force, and this causes the cloud to begin to collapse and shrink under the force of gravity. As it shrinks, its density increases, which causes the cloud to fragment into smaller clumps of gas, which themselves begin to collapse under gravity and fragment again, and so on and so forth in a cascading effect. Now, eventually, these clumps of gas become so dense that you can form stars. And once you start forming stars, they emit energy. That energy blows away the rest of the molecular cloud, and we're left with a group of young stars, which we call a star cluster. So we know this basic story, and we do know a lot of the physics of what's going on during this process. But it turns out we don't really understand all of the details exactly of how to go from a molecular cloud to a star cluster. And that's because there's a lot of different physics involved. Things like the chemistry of the molecular cloud, the thermodynamics of the cloud, how turbulent the cloud is, are there magnetic fields and how strong are they? What exactly are the details of how the stars are radiating energy as they start to form? All of these complicated processes are interacting to form the eventual star cluster that we can see. So it's tricky to understand exactly what role all of these different pieces play. And because stars play such a crucial role in our universe, for example, they create many of the heavy elements that we as carbon-based life forms we require to exist. That, understanding how stars form is critical to understanding how the universe has evolved. So designing models and testing of how stars form and testing those models is a very active field in astronomy. Okay, so a major challenge in all this is that much of our knowledge of star formation comes from studying regions that's close to our very own sun. This is natural. These objects are the closest to us, so they're the easiest to observe. But what happens if we look at star formation elsewhere in the galaxy? What happens if we look at star formation at our galactic center? Well, it turns out the galactic center is a very interesting place to look because it is really a unique environment within our galaxy. And to understand this, I like to think of our galaxy as being a city of stars, right? And in this picture, the sun in our local neighborhood can be thought of as a suburb of this city. So, it's relatively quiet. There's a moderate to low density of stars. And when we look at star-forming regions in our own suburb, or even nearby suburbs in the Milky Way disk, we're not really probing a lot of different environmental conditions. The environment's pretty much the same, similar where we look. But the galactic center, that's not a suburb of this city. It is the city center. It has the highest density of stars in our galaxy, with hundreds of millions of stars compacted in a relatively small area. In addition, you have dense traffic jams of gas and dust crisscrossed throughout the galactic center region. And of course, there's a supermassive black hole, 4 million times the mass of our sun, sitting in the middle of it all. So this raises the question, how do stars form in this really interesting environment that's very different than the environment near our own sun? And it turns out we have different theories for how stars form, and those theories make different predictions on how the stars in the galactic center should be impacted. So by studying the galactic center, we can really provides us an important test for our understanding of star formation physics. Okay, so how are we going to study star formation at the galactic center? Well, we are going to measure a really important property called the initial mass function. Now, the initial mass function, all it is it describes the distribution of stellar masses that are formed in a new star cluster. And this is interesting because when stars form, they can have a large range of masses. You can form really, really high mass stars, say 40 to 50 times the mass of our own sun, and you can form really low mass stars, like a half to about a fifth of the mass of our own sun. And you can form stars everywhere in between. So the mass that a given star forms with is intimately tied to the physical processes that originally formed it. So by studying and learning about the initial mass function, it gives us a window into all the complicated physics going on under the hood when these stars form. And this brings us to our program that we'll be leading right here at UCLA. The goal of our project is to measure this initial mass function of two star clusters that are located near the galactic center, the Arches and Quintuplet clusters that I mentioned earlier. Now, these clusters are among the youngest and densest and most massive clusters we know of in our own galaxy, which really makes them excellent for this type of work. And because they formed near the galactic center, their initial mass function will sample the environment conditions in this crazy region. So the plan, how we're going to do this, is we're going to image these clusters using JWST and very precisely measure how bright the individual stars in the clusters are, because this will give us an idea of what their individual masses are. Okay, so why is JWST an excellent instrument to do this? Well, if we want to study these clusters, we need to have a telescope that has two primary capabilities. First, we need a telescope that has high sensitivity and spatial resolution, so we can observe the stars and resolve the individual bits. And we also need a telescope with the ability to take an image over a relatively large patch of the sky, so we can image the cluster all at once. This is efficient for observing purposes, but it also makes our data analysis a lot easier. So if you want to observe something with high spatial resolution and sensitivity, you really want to use the largest telescope you can get your hands on. For example, you could use the Keck telescopes in Mauna Kea, Hawaii, which here at UCLA we often use a lot in our observations. But the trick with Keck is that because we're observing from the ground, we have to look through the Earth's atmosphere. And due to technical challenges related to this, that means that we're limited to taking images over a relatively small patch of the night sky, much smaller than the size of the clusters on the sky. Right? So Keck isn't really a great instrument to do this sort of work with. On the other side, we can ignore the atmosphere completely and go up to space, and we can observe the clusters with, say, the Hubble Space Telescope. However, and the Hubble can take much larger images, and so that's not a problem anymore. However, Hubble is significantly smaller than the Keck telescopes. I think its area is 14 times or something, 16 times smaller than that of Keck, so you really sacrifice a lot in terms of sensitivity and spatial resolution. So JWST lives in a really happy medium between these two properties. It exists out in space, so we can make images over a large field of view, so that's great. And, as Tommaso mentioned, it's significantly larger than that of Hubble. So it has much higher sensitivity and spatial resolution. It's not quite as good as Keck, but for this project, it really is an excellent instrument to use, and really the perfect instrument to use. Okay, so unfortunately, I don't have any JWST images of my two clusters that I can show today. That's because the data hasn't been taken yet. It's scheduled to be taken in August of this year. But I can give you a little sneak preview of what JWST images at the Galactic Center will look like compared to past Hubble images at the Galactic Center. So here we see a real image taken with the Hubble Space Telescope of just a patch of sky at the Galactic Center. And you can see how crowded this field is, how many stars are densely packed together. So that really makes this work challenging, makes the analysis hard to do. This is the same field taken with JWST. And I'll blink back and forth here because it really is amazing. You can see how much sharper the JWST image is. That's because it has much higher spatial resolution. And we can see fainter stars than ever before with JWST. So I, for one, am very excited to see what these two star clusters will look like in August when we finally get our data. And so that, in conclusion, JWST promises to revolutionize our understanding of how stars form. The project that I'll be leading here at UCLA, our goal is to study the initial mass function of two clusters near the galactic center, the arches and the quintuplet. And by doing this, we will gain a new understanding into all the underlying physical processes that drive star formation. So, thank you. And with that, I think I pass things over to Jean.
Hi, I'm Jean Turner, and I've been in the astronomy department for some time, or physics and astronomy, and lately as chair. And I'm returning now to research, and this is a project that I'm doing with JWST that I was hoping I would get to do, and was lucky enough to I competed with some other groups to get the time on this, and very happy to get this data. So this was entitled Opening Pandora's Box, Discovering the Hidden Content of a Superstar Cluster. And so JWST, the advantage in this case is the fact that it is an infrared telescope, so that we can see a cluster that cannot be seen any other way. And some of the people I am working with on this project and related projects are listed at the bottom, including current and former UCLA graduate students and undergraduates, and some other collaborators that go way back. Okay, so the subject of my study is a large star cluster. And it's similar to the ones that Matt is studying, except a factor of 10 larger, at least a factor of 10 larger. And it's similar to globular clusters. Now, this is a schematic picture. It's an artist rendition that I did of the Milky Way with globular clusters surrounding it. So you see that, whoops, hit the wrong. Okay. All right. So this is the globular cluster system of our Milky Way, which forms a sort of sphere centered on the galactic center. And they're very beautiful and very giant clusters. And they're ancient. So all of them are close to the age of the universe. They're all over 10 billion years of age. So this is the ancient fossil record of what the Milky Way originally was. And there are many people who think, and I think the odds are, that star formation in the early universe was in the form of these giant clusters, like globular clusters. So our galaxy is no longer forming clusters of this size. It's no longer forming globular clusters. The largest clusters are the ones that Matt has seen in the galactic center. And they're slightly smaller, and they're also in the galactic center, so it's not quite the same thing. So we're very interested in how these formed. Now, why? This is a mystery, really. Let's see. Okay, yes. This is a globular cluster, and this is very similar to the one I hope to observe with JWST. So this is 10 billion years of age. This is M15. You can see there are a million stars here. And that described the process of star formation, where gravity wants to pull in a gas cloud and pressure pulls it out. If it manages to collapse, you can picture how it wants to form a sort of spherical object like a star. Forming a million spherical objects, why does it do that? That's a real mystery, and it would be wonderful to actually see one of these huge clusters forming. With JWST, we have a hope of doing that. Okay, the big questions. And what I mean here are not the big questions, but the big questions. First, how big can a globular cluster be? We know that there seems to be a cutoff. This M15 cluster is about as big as they get. They get to be, the limit seems to be about 500,000 solar masses. So there is a limit on their size. What causes that limit? Okay, what stops them from growing? We think we have an idea, but I'm not really convinced of this. And this cluster I'm going to show you might be a counterexample. It might be doing something different. The second question is, how big can stars be? Now, the biggest stars don't live very long. They are very rare, just because they burn out fast. And so it's hard to understand how even the stars that we see, the massive stars we see, have formed. But there is a belief that stars could get to be 300 times the mass of our sun. We don't see these currently, but currently it's the limit is maybe at 90 to 120 solar masses is what we see, but there might be even bigger ones. And so the fact that now that we see with the LIGO gravity wave detector, we see massive black holes. We don't know how they formed through stellar evolution, kind of points to the fact that maybe there are these massive stars out there, and they're hard to see. Statistically speaking, you would expect to see one in a cluster like this, where you would not expect to see it in the small clusters of the Milky Way. Okay, so where does Pandora's box come in? There actually is a connection here. Zeus, just a reminder, Zeus gave Pandora, the first woman, not to Prometheus. He was ticked off at Prometheus, but to Prometheus's brother. And Pandora came with a box, and Prometheus warned his brother about the box, but he opened it up, and of course it had all the evils that got dispersed into the world, and he closed it up, and apparently hope was left. So how does Pandora's box relate? It does, because within a young cluster there are dangers that await young stars. So what are these dangers? Okay, first of all, let's talk about massive stars, how many there are. They are rare objects, but 1 out of 100 stars will be an O or B star. And those, after 3 to 4 million years, will go supernova. And that's how we expect that most clusters clear themselves of gas. Is that they last 3 or 4 million years, and the first few supernovae will just clear them out. Okay? out of every 1,000 stars will be a Wolf-Rayet star. They have winds. They lose 75% of their mass in heavily enriched winds. So they've been fusing all these elements, and they put out these very, very metal-rich, we call them metals, I'm not supposed to call them metals, things like carbon, nitrogen, oxygen. Okay, and then they go supernova. And then finally, one star out of 1,000,000 could be a 300 solar mass star. Okay, so what's the big deal about O stars? They're very destructive. And so if you look here are the different ways across an O star's lifetime that it can be destructive. First of all, when it's forming, it has these jets that come out, accretion jets. Those probably don't, from what we can tell, don't dissolve the cluster. The next one over, going clockwise, well, to the right, is the Homunculus Nebula, which is a luminous blue variable, and this thing had a big outburst about 150 years ago, and we see the evidence of it in this nebulous, amazing nebula. It's actually in the picture that Matt showed of the nebula. You showed it, it's in there. Down in the lower left is a Wolf-Rayet star with all of its wind that it's putting out. And then on the lower right is a supernova, and that's a big blast wave that just sends things out, shocks the gas, heats it to 10 million degrees, etc. Now, at the bottom here, I have a circle, and that is 1 parsec, or about 3 light years. That's the size of a core of a globular cluster. And that core will have 1,000 of these stars. So just imagine the environment there. It's incredible. So how do you form 1,000,000 stars in this environment? Because it takes a while to form a star. It takes maybe 500,000 years to form a star. And if they only live 3 million years, that's a simultaneity problem. So either the young embedded cluster must be very young to see it still forming stars, so that Wolf-Rayet stars or supernovae have not had time to develop, or if the cluster is sufficiently large, it can self-pollute in heavy elements so much that it stalls the stellar winds. So this was a model that was actually developed based on the cluster I'm going to show you. The fact that it might be confining the winds, it might allow the cluster to grow. Okay, and who knows what might happen. So here's this model. This is the model that most people assume is that these stars will blow out bubbles around them, the bubbles will merge, and so when you have a cluster, you have this big environment with a lot of hot gas inside surrounded by a molecular cloud. That is not our thinking. Our thinking is that each individual star has its own cocoon and that it protects the other stars and allows the formation to continue. So that's the model. Here's the galaxy. This is the galaxy. It's our target, NGC 5253. It's a dwarf spheroidal galaxy, so it has very little gas. And it's also tiny. It's maybe 100th to 1,000th the size of the Milky Way. So it's not where you expect to see one of the most massive clusters in the local universe forming. It has an amazing nebula that's been known for a long time. So we're going to focus now, from now on, the images I'm going to show you come from this little red box, this tiny little region around this forming cluster. So here's a picture. Now this is a picture taken by HST in the line of H alpha, which some of you may know. It's a red line that traces nebular gas. So this is produced by ionizing photons from O stars. And this is the central region, and I will show you about the size. So I've got up in the left-hand corner, I've got 50 light years up here. The Orion Nebula, which you saw in a previous slide, is tiny. It's about a parsec. So that, and the core of a globular cluster is about a parsec. So it's very tiny compared to this. Well, let's see, this is 50 light years, so it would be 3 light years. 1 parsec, 3 light years. Okay, so where is the cluster? We see this beautiful, beautiful nebula here, where is the giant cluster? And for years I argued with people at HST that it was this thing, and I said no, it wasn't. And in fact, it turns out it's here. So this amazing cluster is right here. It's totally embedded. HST cannot study this source at all. Okay, so let me show you to prove this is a radio image. You see the contours. This is probably the highest resolution image ever made with the Very Large Array in New Mexico. It's a radio image. Radio can come right through the dust. And so we see this nebula. Radio emission's very weak, so if you see something this strong, it's an amazing source. I observed it with the ALMA telescope in Chile, and I got a picture of the molecular gas, and this is a picture of the molecular gas. So Matt showed a picture of a molecular cloud that was dark. These are contours. This is in the line of carbon monoxide, which traces H2 gas. H2 is kind of hard to see. And, whoops, let's go back. All right, so this is H2 gas, and you can see this is just what we expected to see because there's dust blocking this thing. So there's a CO cloud surrounding this. So it is a forming superstar cluster. It's massive. We can measure the mass with the CO, and it's roughly 500,000 solar masses. So it is at the limit of what we expect to see for a globular cluster. So it's forming, and the CO is remarkably quiet. No evidence of any winds or anything else coming from the CO. So this is puzzling, and it led to some of these models. So this thing could still be forming stars. It is still forming stars. If we could see magically what this would look like, this is a picture of what's going on. So you have this cluster here behind the CO cloud. There's another CO cloud, I'll mention this later, nearby, but it's not connected. This thing is the forming cluster, and if you could see through, that's what you'd see. It's the core of a giant cluster. So what is JWST going to do for us? And if it was 6 months from now, I could show you data, but I can't. I've just gotten it. I got some of the last of it about a week and a half ago, and it needs processing. So I can't show you, but I can show you sort of what we expect to see. Okay, this is a spectrum of Spitzer Space Telescope, from Spitzer Space Telescope, which has 50 times less collecting area than JWST, but it's a nice spectrum. And it was a single slit covering most of the galaxy, so we can't separate out the giant cluster from all the other clusters that are there, but we do see many lines. So we're going to see a spectrum that looks like this in the middle infrared. This can get through that amazing dust cloud. Here is what JWST is going to be able to tell us. It's going to be able to tell us where the hot stars are. So, okay, and the MIRI instrument on JWST doesn't just take a slit spectrum. So that's a 1D spatial information where you get a spectrum along the long slit. No, JWST actually takes images. So for each one of these lines, we will have an image of the region I showed you, the entire region. And so we'll have tremendous amount of information. So we'll be able to look at the hot stars with these lines, the hotter stars with some of the other lines. We'll be able to look at the dust here. We'll be able to look at polycyclic aromatic hydrocarbons, which are very large molecules which will exist at the molecular cloud nebular interface. We'll be able to detect hot molecular gas. So we'll get all of this information with spatial maps. So we'll have hundreds of spatial maps to look at of that region. Now the final thing that's really interesting about this source, and I'll show you, and JWST may be able to tell us about this or not. We think that this star formation is actually fueled by gas falling into the galaxy, which makes it unlike any other star forming region we've studied, and much more similar to what we think was happening in the early universe. So if you look at this, it's kind of hard to see. It's dim, unfortunately. The background is an HSD image of NGC 5253, the stars. So this is the stars. And the red is carbon monoxide. This was done with this Smithsonian submillimeter array. And so this is CO. So this is where the molecular star-forming gas is. Very bright here, but you already saw, I showed you the picture of the CO from ALMA, which is this source here. It's very hot gas. Most of the gas is out here. And this is falling in. We can tell by the Doppler shift. It is falling in. We think this is fueling that star formation. And that could be why it's different. JWST may show us evidence that that's happening. We can't prove it. We say we think this is fueling the star formation. People say, yeah, right, circumstantial evidence. But I think JWST may help. So unfortunately, although I have the data, I have raw data, it needs to be processed, so I wouldn't do it justice if I showed it to you. But what I managed to do was figure out a way to show you some of it. So I applied a Photoshop filter. Actually, it's Pixelmator. This is the actual data, and I applied a filter. But this shows you, this shows you here the pixel size. So you can see that each one of these pixels will have a spectrum. You see the immense amount of information that we have, and you can see the peaks. So I will show, here's the peak. You can see in the background in gray is the previous image I kept showing you of the HST image of H alpha, and on top of it is the JWST data. And you can see the bright highlight regions. You can see we're detecting this. Even in the raw data, you can see it. And this is a particular spectral line, and if you can figure out what the filter is, you will know what line it is. And I bet you Ned Wright can do that. So, thank you.
Okay, so my name is Guido Roberts-Borsani. I'm a postdoctoral scholar over here. And today I'm going to take you right to the very edge of the observable universe and tell you a little bit about one of the programs that we're leading over here at UCLA, trying to confirm the distances to and characterize the properties of some of the most distant galaxies in the universe. And you know, in my field, when we talk about distant galaxies, we typically refer to galaxies that formed sometime within the first billion years of the universe. And within just the first 6 months or so, James Webb has completely revolutionized our field. And I think one way to illustrate this really is the last cycle that we had for James Webb proposals. I was discussing with Tommaso over here whether we should concentrate on galaxies that formed maybe 300 to 400 million years after the Big Bang, or ones that formed sort of 800 million years after the Big Bang. That doesn't sound like a lot of time, but there's a difference between the two. And the reply I got was, Guido, 800 million years was so 2 months ago. So that really just highlights how quickly this field is going. So to put things into a little bit of context, this is a nice schematic that shows you the history of the universe. The universe is about 13.7, 13.8 billion years old. Time is going from left to right. So over here, our universe started with the Big Bang as we know it. That Big Bang left this beautiful imprint here, shaded by the blue and the yellow, which is the cosmic microwave background. It's the imprint of the Big Bang. And there were no sources at this point. After that point, some 380,000 years after the Big Bang, we entered a period called the Cosmic Dark Ages. There's a complete absence of stars, of galaxies, of any kind of structure as we currently know it. But sometime within the first 100 million years, the very first stars formed, as we heard via the processes that Matt and Jean have described. And those stars formed clusters, and those clusters of stars eventually formed the very, very first galaxies within that 1 billion year time frame. And eventually those galaxies evolved, and they now look like these very nice structured spiral galaxies, much like our own Milky Way. And so we want to understand how those galaxies formed and evolved over especially that very early period. And what you might notice over here as well is there's this kind of middle point over here where there seems to be a lot of fog, if you want. And this fog is actually the hydrogen left over by the Big Bang. And this hydrogen basically is getting burned through by the very first sources. So if we want to understand, or if we want to gain a coherent picture of the universe, we need to understand how these first galaxies altered the fabric of the universe. So up until now, our flagship telescope has been the Hubble Space Telescope, and James Webb already is going far beyond what Hubble was ever able to do, and with its imaging from NIRCam, for instance, one of its imaging instruments there, finding galaxy candidates out to, when we talk of redshifts greater than 10 or so. So that corresponds to galaxies within sort of the first 500 million years of the universe, when the universe was only 3 to 4% of its present age. But crucially, these galaxies remain candidates. They are not confirmed yet at the distances that we think they might be. And so what we really need is a spectrograph. This is the cosmic fingerprint, if you want, of galaxies. And so these spectra that we then obtain with James Webb allow us to answer these questions. When did the first stars and galaxies form? What were their properties? Which elements did they have? What were their chemistry? Did they render the universe transparent, like I showed you in the previous slide? And ultimately, did they have supermassive black holes? When did the first supermassive black holes form? So for me, this is one of the most stunning pictures that we got recently with the James Webb telescope. This is a NIRCam image over several different filters in the infrared over Pandora's cluster. And you can see this cluster over here, this part of this more extended cluster over here was studied extensively by Tommaso's ERS program. And what you might notice is there's a huge variety of galaxies that have this very nice sort of structures over here, galaxies that are blue, galaxies that are very red. And what you might see, it's a little bit difficult over here, but some of these galaxies are stretched by the gravity of these foreground galaxies. This is a phenomenon we call gravitational lensing. And behind here, you have some of the most distant galaxies we currently know of. And over here are 7 different examples. Now, these objects might not look like much, but they are in fact baby galaxies. These galaxies, we see their light as it was only 500 million years after the Big Bang. So this discovery was made by our collaborators in Rome and ourselves at UCLA as well. But all of these galaxies remain candidates and need spectroscopic confirmation. So we talked briefly about spectra. I think Pink Floyd, when they released their album, didn't realize that they were releasing one of the best albums of all time, but also that they were giving us a very valuable lesson in physics and astronomy. And that is that white light actually consists of all of the colors of the rainbow and beyond. And when you use a prism or a grism, for instance, and you split this light into its constituent frequencies, you can start to see the imprint of elements on those spectra. So the imprint of hydrogen, nitrogen, oxygen, neon, etc. Now these are not just random spikes. These are really the cosmic fingerprints of the elements on a spectrum. And our job as astronomers is to try and decipher what we see on these spectra here. So one question which arose earlier was, why can't we do this from the ground? James Webb is a very expensive telescope, but we also have wonderful ground-based telescopes in Chile, for instance, the Very Large Telescope, Keck in Hawaii. And the reason is because we have our atmosphere. Earth's atmosphere, unfortunately, blocks most of the infrared light where these distant galaxies emit the majority of their light. So you can see here our atmosphere. This is the type of light on the x-axis and the distance from Earth on the y-axis. UV, X-rays, gamma rays are completely blocked. They do not get down to our telescopes. We can see some of the optical part of the spectrum over here, some of the infrared, but most of it gets blocked, or a lot of it gets blocked. And so that's why we need a space-based telescope like James Webb to be able to take spectra of these galaxies in the infrared where they emit the majority of their light. So only 6 months after we started collecting data in December, James Webb wowed the the field of high redshifts or very distant galaxies by finding 4 of the most distant galaxies we've ever seen. These are with confirmed distances. So this has broken the distance record, not just by a little bit, but by a mile. Over here you can see the portion of the sky over which they're found. You see these 4 galaxies here from the bottom to the upper panels in order of distance. You can see that they're very red, they're very small, there doesn't seem to be anything particularly special about them. But if you take a spectrum of them, this is what these spectra look like, and you see this is in 1D here, so the brightness of the galaxy is on the y-axis, the wavelength in the infrared on the x-axis. Now the spectra don't look, particularly impressive in a way, but actually what you might notice is there's this break, this characteristic break at the left side of these spectra, and the position of that break tells us the precise distance of these galaxies. So these galaxies are found when the universe was only 300 to 400 or 300 to 500 million years after the Big Bang. So 3% of the age of the universe. But these galaxies were all found in a very small part of the sky. So you can see here the moon to scale and basically the area of that field which imaged these galaxies. And that's like if you were to take a pen, keep it at arm's length and look at the tip of that pen. That is the equivalent of the area probed by that survey. So how do we know that these galaxies are representative of the general population? And this is, I think, nicely illustrated by this plot over here. This is a plot of a simulation of our universe on the biggest scales, really, really large scales. And what you're seeing are clusters of galaxies in sort of the orange. And if you were to point your telescope at one part of the sky, you might see an abundance of really, really distant galaxies, like I showed you previously. But if you were to point it at just another part of the sky, you might not find a lot of distant galaxies. So how do you know which ones are representative and which ones aren't? So we tried to address this at UCLA. First with Hubble, basically we conducted the largest space-based search for very, very distant galaxies that formed sometime within the first 700 million years of the universe. You can see this is the survey area of those 4 galaxies that I showed you. These are individual pointings of Hubble. And so you have this kind of trade-off where with a telescope like Hubble, you can either point at one part of the sky for a very, very long time and try and build up area. That means your area is not particularly large, but the depth of your observations are very, very deep. Or you can take single pointings like these and map them all across different portions of the sky, just like I'm showing over here in the bottom plot. So this represents the Borg survey, which tried to do that. That's an acronym for the brightest of reionizing galaxies. This is the survey that we led at UCLA, and every single red point represents one Hubble pointing across the plane of the sky. And we found 32 of the most distant galaxies known at the time. Here I'm showing you 5 different examples. These are filters from the Hubble Space Telescope, going from the optical on the left all the way to the very near infrared on the right. And what you might notice is that these galaxies are all seen in the very near infrared, and that's because that's where they emit the majority of their light. But in the optical, they all disappear. And that's basically because of their characteristic signature that I showed you before in the spectrum, that drop in the light of that galaxy. So the location of this dropout gives you an approximate distance to those galaxies. And so the program that I'm leading is to try and confirm the distances of these galaxies and study their properties so that we understand what representative samples of very distant galaxies look like. And this is the NIRSPEC instrument on the James Webb Space Telescope. It's an infrared spectrograph, basically gets you a spectrum from wavelengths of 0.6 microns all the way out to about 5.3. And over here, these 4 quadrants are what I would bring your attention to. These 4 quadrants are made up of hundreds or thousands even of very small slits. And those small slits open up on the position of a galaxy and disperse its light to reveal spectra that I showed you before. And so we have about 25 hours. It's a medium-sized program to target 10 of those very distant galaxies that we found with Hubble to try and study them. And now this is a simulation of what we expected to get. This is the 2D spectrum, and if you project it to 1D, you see this break, which I showed you before. But crucially, you also start getting the imprint of ionized oxygen and ionized hydrogen, really the chemical evolution of these galaxies. And we can, for the very first time, start answering questions such as these questions here. When did the first stars and galaxies form? What was their chemical enrichment? You know, really the basic, the building blocks for life as we know it here on Earth. It's a study really of our own chemical history. Did they ionize the universe, and did they have supermassive black holes? And now we can insert them into these quadrants, and we can actually get hundreds of spectra all in just one exposure. Now this was unheard of really beforehand. Okay, so I showed you one galaxy actually just beforehand. So this is data that came in over just the last weeks. We observed this with James Webb, and this is actual real data. This is the spectrum that came through. So we could only dream of this decades ago. Astronomers in my field have been dreaming for this for decades. You know, I wasn't even born when the James Webb the idea was first conceived, but I like to think my cells were probably dreaming of it as well. And you can see how this has very particular signatures. This break over here gives you the exact distance of the galaxy. So it's a galaxy that's seen 600 million years after the Big Bang. It's very precise. We have the signatures, the cosmic fingerprint of ionized oxygen and ionized hydrogen. So it's saying that this galaxy is already chemically evolved. We also have the light from young stars, so we can get the rate at which this galaxy is forming young stars. And we also have the light of older stars, so we can try and trace the bulk of the stellar mass of this galaxy. And this is only the first one out of the 9 that we still have to come. So I'm going to leave you here with this beautiful spectrum and say that, you know, only within the first 6 months, James Webb has completely revolutionized the field of distant galaxies. And very fortunately, UCLA is playing a very strong and leading role in not just proposing these projects, but also designing them and analyzing the very first of these extremely exciting data sets. Thank you.
All right, so thank you, Guido. Thank you, Matt. Thank you, Jean. That was exciting. So we have time for a little Q&A now. So I'm sure there was a lot. So yes, please.
How big is the field of view of James Webb, and how does that compare to the clusters that Matt's looking at?
I'll repeat the question for those of you online. So how big is the field of view of James Webb, and how does it compare with the cluster that Matt was studying? So Matt doesn't have a microphone, so if you want to come over to here.
Yeah.
So the field of view is order a few arc minutes, but Matt can say how big it is compared to the clusters.
Yeah, actually, it's a very good size match. So the field of view for the JWST is roughly 2 arc minutes on a side. That's the same width. I calculated this beforehand. If you hold a birthday card and hold it out at arm's length, like that thickness, imagine that as a little box on the sky. So that's it. Now, in terms of the clusters are about that same size, actually. So within that 1 2 arc minute by 2 arc minute box, we're able to observe the stars pretty much to the edge of the cluster. So it really is a nice match.
Thank you, Matt. Any more questions? Yeah, please.
Yeah, my question goes more to the operation of the particular arrays. So to the 3 speakers, for somebody who actually helped build the JWST, I wondered how well it works. And to be more specific, NIRCam is the one that I worked on. And what did you find with it as far as how much noise it produced, how much sensitivity it has, how many photons per second it can pick up reasonably well? Just in general, you know, when you turned it on, this is how well and what you expect.
Okay, well, thank you. So the question was, so this gentleman has helped build NIRCam. Well, thank you so much. And so he was curious about the performance of NIRCam. Maybe I can answer that. And then if you guys want to add anything, that's you're welcome. So it performs extraordinarily well. So the sensitivity is higher than specs. The one thing that is a little surprising is there's a noise called a 1/f noise that shows up in the data. So we had to learn how to correct that. And there's a series of anomalies that have funny name like dragon claws or whisks or other things. And those come from a variety of things, from electronics to scattering of light to other things. So we're still working out how to correct all those things, but I would say nothing fatal. Like, these are all things that are common in space-based instrumentation. You know, space is a very harsh environment. And so I would say it's performing better than anyone of us dreamt before launch.
And you didn't see any hot pixels?
There are hot pixels, of course. There are defects. There are snowballs. There are a lot of little things, but nothing, I would say, unheard of and nothing too concerning.
Because we rated it at about a photon a sec. Do you still believe
Yeah.
that?
Yeah. No, the performance is better than specs. So I think we're very happy with that.
Yeah.
So thank you so much.
Yeah, it was difficult.
I'm sure it was. So kudos.
You think 3 in the morning is something big? That's what I would think.
Yes.
I have one more question. How would you compare you showed some NICMOS data, right?
NICMOS?
Hubble.
Maybe
With
C3. With C3 IR.
Yeah, I thought that it looked like NICMOS data.
No, it was the with C3 infrared channel.
Did you guys ever put NICMOS data against JWST
Oh,
and measure it that way?
that would be cruel.
Right.
Well, NICMOS performance is so much.
Careful, I worked on that one too.
No, I mean, but NICMOS was installed in 1997. What was it, right? So obviously, there's been progress in detector technology. You know, it's a much more advanced detector on NIRCam, much bigger telescope. So I remember we were trying to do high redshift galaxies with NICMOS 20 years ago. It was really hard.
Yeah, well, the duration on station with the resolution, it was just a 1K.
Yeah.
1K
Yeah,
by
exactly.
1K. And I
But
always
also the
wondered-
level of defects. I remember early on working on NICMOS 20 years ago, and the amount of defects on NICMOS was much worse than NIRCam. Like, there were all sorts of like electronics. I might remember pedestal ghosting, all sorts of things that happened on NICMOS that we don't see on NIRCam. So thank you.
Familiar with the term persistence, right?
Yes,
Did
persistence.
NICMOS produce that much persistence?
NICMOS did. NIRCam, I haven't seen it yet. We were worried at some point that there may be. In some of my early data, I saw something, but it turns out there was a event where one of the mirrors had a little flick like that, and that created something that looked like persistence, but it wasn't. So far, no sign of persistence
Yeah,
here.
because the general construction between them two is
Right.
very different.
Right, exactly. So yeah, we have a question here in front.
Yeah, what is the nearest star that's 300 times, let's say, the mass of the sun, and how does that distance compare to the Polaris A star, what we call the North Star?
Okay, so the question is, how far is the nearest star that is 300 times the mass of the sun? I don't think there's any. We don't know any of one.
We haven't detected one.
Yeah.
It is,
Would
I
it-
think it has been suggested in the cluster I'm looking at in the galaxy, which is 12 million light years away.
Yeah, so
So that
just
is
let me
likely
summarize this in the microphone.
closest.
Jean just said that we don't know any such star, and if there is one, she thinks it's in Pandora's cluster. And just to clarify, we had Pandora's cluster and Pandora's cluster, they're different clusters. So the one that Jean was talking about is a star cluster. The one that Guido was talking about was a cluster of galaxies. So they're completely different objects. I'm sorry, we should be more creative in our naming, but just to clarify the confusion. Ned, you had a question?
Yeah, so with these Borg galaxies only being 31 in all those fields, it seems like you'll only be able to do one object in a pointing with the mirror spectrograph. But then you could set up a whole bunch more for near spec. But anyway, so you have all these shutters. How do you pick other objects in the field? to
So
use?
Guido, do you want to answer? The question was, yeah, you heard, it was to the microphone, so.
So the proposal revolves around the most secure selections that we have, and we tried to be as secure as possible when we did this search for distant galaxies. There are other ones within some of those fields which perhaps are slightly less secure but could be distant galaxies. So we insert those into the MSA as well. And then part of the survey is also we want it to be a little bit of a legacy survey, in the sense that we fill the MSA with whatever else we can find, whether it's galaxies at redshifts sort of 2 to 3 that are star forming, passive galaxies, stars, everything we can select, we put in there, but the priority is those 10.
Oh yes, there's a question there in the back. Yeah. Wait for the microphone, please.
I heard recently that, as was mentioned on the news, that JWST took a micrometeorite hit that was larger than they were expecting at this juncture in its lifetime. And then there was another article that said if there were like over a dozen of these, that it would basically invalidate the results. Or can you comment on that?
Well, certainly there was a hit that was larger than expected at this stage. But remember that all these predictions are statistical, right? So there's kind of like when you win a lottery ticket, you don't expect to win, but sometimes you do win. So I think the problem is that we are aware the micrometeorites are potentially an issue for the mission and may be fatal at some point. But there's a statistical confidence that there will not be any significant hit that damages the mission in an irreparable way. But we only have a statistical analysis of that. Maybe this gentleman wants to comment on that.
I can address to that.
Yep.
You're familiar with how the mirrors are built.
Wait for the microphone, please.
Yeah, you know what, that particular mirror strike, the actuators were able to take that out, to essentially refocus that particular mirror. There are 18 of them around, and you could selectively remove one mirror and not really degrade the performance that much. But the last time I looked at the reports, the hit was not enough to really damage the mirror so badly that it had to be removed.
Yeah.
Defocused, if you will.
So far so good. Of course, the sun shield, and that's an issue as well, but we'll see. Yeah. Any other questions? Oh, okay. One more question. Go ahead.
Yeah, it's one of the. I wondered if there. I think most of us see this, but recently there was a 60 Minutes article, and they found a distant galaxy that was extremely redshifted, and the distance, not the time, but the distance, it was put at something like 33 billion light years away. Okay, I wondered if you guys concur with that estimate.
So there's several. I haven't watched 60 Minutes, so I don't know exactly what you're referring. Have you, Guido?
I haven't watched it, but I know which one you're referring to.
Yeah.
And it was the 4 galaxies which I showed earlier from the good sphere.
Guido, do you want to speak into the microphone?
Yeah.
But they're not at 33 billion years away. That they're at the time frame. They're at redshifts basically 10 to 12 more or less, which corresponds to 13.5 billion years away, something like that.
Okay, that's quite a different. I'm looking at you as an expert.
So maybe we're confused about. There's many different distances. There's a distance there's the distance that the light travels to us, and then the distance that this galaxy would have to us today, right? You have to imagine that after the light leaves the source, the universe is expanding. So the galaxy would be more distant to us than it was when we observed it.
Yeah.
So Guido's talking about the light travel time, which is about 13 billion years.
Right.
And I guess you're probably talking about the present day distance, which is...
Essentially you have a galaxy that formed something close to the edge of the Big Bang, 300 million years plus, whatever. So we see that light, and in the meantime it's traveled another 13 billion years.
Right.
So if you add 13 and 13 together, you get something close to 30.
It doesn't exactly work like that, but because what happens is that the universe is much smaller at redshift 10. Is a factor of 10 or 11 smaller.
Yeah.
So everything is closer by. But then as the universe expands, light travels toward us, and the distances between galaxies grow.
Expands.
Right. So the present day distance may be significantly larger than the distance traveled by light.
Right.
Okay.
But you don't concur that it's on the order of 30.
I haven't done the calculation. I mean, maybe we can do it offline after. But
The internet says it's 30.
okay. Well, you can find a lot of things on the internet that are correct and a lot of things that are incorrect. So maybe Ned has his calculator here. He can do it for us.
Yeah, you could use my cosmology calculator.
Ned wrote a very convenient Java-based calculator where you can plug in the numbers and get the answer. Yeah.
I'm sure that the reporter did that too.
But in cosmology, there's many distances. We have to be a little careful about what distance we're considering. So, any other questions? Yes, we have a question there. So I think we have time for a couple more questions.
You keep using redshift as a proxy for distance and age. Does velocity just go up? How is that?
Yeah, so the typical velocities at which galaxies move with respect to what we call the Hubble flow, the rest frame of the universe, are of order a few hundred kilometers per second. And those are completely negligible with respect to the cosmological redshift, which is the stretching of light by the expansion of the universe. Yeah. Any more questions? Well, we were either completely clear or completely obscure. So, yes.
Well, you mentioned different distances. So now you've got me thinking, well, how far away was the galaxy that you showed the picture of at the time?
At the time of what?
13.5 billion years ago. How far was that galaxy from us?
We weren't there.
We weren't there.
Oh, the Milky Way hadn't formed yet. Well, we could say where it is.
Okay, the point, I don't know, I haven't done the calculation. It's probably, if he is right that it's 33 billion light years now, then you divide that by 1 plus z, like what, 14, and you get the answer.
Wait, I didn't say it was 33. I just reported it.
Okay, if it's really 33, you divide that by 14, so it's about 2. But, you know. Oh, no. Okay, well, it seems like we have to use Ned's Java-based calculator during the reception. Yeah. Any other questions? Well, it was wonderful to see you all, and those online. Thanks for zooming in. And thanks to all the speakers. And stay tuned for more results from JWST.